Welcome to the deep dive. We get straight into complex topics and make them really clear and insightful for you.
Yeah, cutting through the noise.
Exactly. You're here because you want that knowledge quickly. You appreciate those aha moments, but you don't want to feel, overwhelmed by jargon.
Absolutely.
So today we're taking a deep dive into making high-strength titanium alloys tougher, specifically against fatigue.
Which is a huge deal. Fatigue failure, that's when materials just break down from repeated use or stress over time. It's a massive problem.
Right. Think airplanes, cars.
Even medical implants. It hits safety, reliability, how long things last. And titanium alloys, they're amazing materials, strong, they don't corrode easily, they're biocompatible.
But still room for improvement.
Definitely, especially in fatigue strength. We've been looking at a study from Fruiteria.com that outlines a really novel approach here.
And the exciting part, they're actually aiming to get this commercialized pretty soon, like 2025, 2026.
That's the goal, yeah. So it's not just lab theory.
Okay, so our mission today, pull out the key insights from this research. How are they planning to get past old limitations? What improvements can we, realistically expect?
Let's get into it.
All right, so first off, what's the fundamental problem they're wrestling with here? This fatigue failure in titanium.
Okay, so fatigue fracture. Think of it like bending a paperclip back and forth. Eventually, it snaps. In these high-tech alloys, it happens in stages. First, a tiny, tiny crack initiates somewhere. Then, with each cycle of stress loading and unloading that crack propagates, it grows a bit. And finally, it reaches a critical size and you get the final sudden fracture. The whole thing breaks.
Which you really don't want in an airplane wing.
Or an artificial hip.
Yeah.
So the challenge is to improve resistance at every stage, make it harder for cracks to start, slow them down if they do, and just push that final fracture point further out.
Making things safer, last longer. Makes sense.
Yeah, it translates directly to reliability.
So this study proposes what? 4 main ways to tackle this? 4 pillars, they call them.
That's right. 4 key innovative approaches working together.
Let's break down the first one. Grain refinement and grain orientation control. Sounds microscopic.
It absolutely is. We're talking about the structure of the metal itself, down at the grain level. Grains are like the tiny crystals that make up the metal.
Okay.
They're aiming to create ultra-fine grains, like 1 micrometer or even smaller. That's incredibly tiny.
Wow.
And the core idea is these super small grains make it much, much harder for those initial fatigue cracks to even get started.
So smaller is better. Why exactly? The study mentions the Hall-Petch relationship.
Yeah, yes, Hall-Petch. It's a classic in material science. Basically, it quantifies how grain size affects the material's yield strength. That's the stress it takes to permanently deform it.
Okay.
The formula looks like zero plus KED to the power of -1/2. So zero is yield strength, SIR is a base strength, K is a material constant.
But the key part is D, the grain size.
Exactly. And notice it's D to the -1/2, or 1 over the square root of D. That means as D gets smaller,
The strength goes up.
precisely. Tinier grains mean more grain boundaries packed into the same space. These boundaries act like little roadblocks for dislocations, defects moving through the material, which is how plastic deformation happens. More roadblocks, harder to deform, higher yield strength.
Like a wall made of smaller, tighter bricks. Harder to push over, harder to start a crack in.
That's a great analogy. So making grains ultrafine directly makes it harder for those initial fatigue cracks to form because the material is inherently stronger and resists local deformation better.
Okay, that clicks. Now, the second part of that first pillar was grain orientation control. How does arranging the bricks, the grains, help?
Right, so it's not just size, it's also how they're lined up, their crystallographic orientation. If you can control this, you can actually influence the path a crack takes once it starts growing.
So you can steer it.
Sort of. You can make the path much more difficult. Imagine aligning the grain so the crack is forced to constantly change direction, twist and turn, maybe get deflected or even arrested at grain boundaries that are oriented unfavorably for crack growth.
Like building a maze for the crack.
Pretty much. You're inducing crack dispersion, making it harder and slower for the crack to propagate through the material, which delays the final failure.
Okay, technically then, what are the big pluses and maybe the hurdles with this grain control approach?
The big advantages are clear. Higher resistance to crack initiation due to small size, and higher resistance to crack propagation due to the controlled orientation. Big wins for fatigue life.
But the challenges?
Well, Actually making materials with uniformly ultrafine grains and precisely controlled orientations, that takes some seriously advanced manufacturing tech.
Right. Not easy.
Very precise control over heating, cooling, deformation processes. And getting that perfect microstructure throughout a complex part, not just in a small sample, is a major hurdle. It's powerful, but technically demanding.
Okay, let's move to pillar number 2. Alloy composition design and elastic modulus control. Elastic modulus. That's stiffness, right?
Yep. How much it stretches or bends under a given load. It's a fundamental property.
So how does tweaking the alloy's recipe, its composition, help with fatigue?
The idea here is that by adjusting the elements in the titanium alloy, adding a bit more of this, a bit less of that, you can actually fine-tune its stiffness, its elastic modulus E.
And you want to change it how?
Hmm.
Stiffer, less stiff.
Often, the goal is to actually lower the elastic modulus somewhat,
Really? Why lower?
because a material with a lower modulus is, well, more flexible. Under the same stress, it will deform slightly more, which can help to distribute the stress more evenly and reduce stress concentrations.
Ah, those hot spots where cracks like to start, like the sharp corner on that tearing paper analogy.
Exactly. By relieving those stress concentrations, you make it harder for fatigue cracks to initiate. The elastic modulus is basically a function of the alloy composition and the temperature, so EF composition temperature.
So changing the ingredients gives you another knob to turn, controlling stiffness to fight fatigue. The study mentioned aluminum and vanadium.
Yeah, those are common elements in titanium alloys. Adding aluminum, for example, tends to lower the elastic modulus of titanium. Vanadium is another one they can adjust to fine-tune that property, often aiming for that sweet spot of stiffness that minimizes stress peaks.
Feels like a balancing act. What's the main advantage and, I guess, the catch with fiddling with the composition?
The advantage is flexibility. You can potentially tailor the modulus quite precisely by adjusting the alloy chemistry.
But the catch?
The big limitation is that changing the composition almost always affects other properties too. You might lower the modulus, which is good for fatigue initiation, but you might accidentally decrease the overall strength or make it harder to process or affect its corrosion resistance.
Right, you fix one thing and potentially mess up another.
It's always a trade-off in material science. You have to find that optimal balance for the specific application.
Okay, third pillar, fusion of surface hardening technologies. This sounds more straightforward, making the outside tougher.
That's the core idea, yes. But it's a bit more sophisticated than just making it scratch resistant. These techniques do increase the surface hardness, which helps resist wear and initial crack formation. But critically, they also introduce residual compressive stress into the surface layer.
Compressive stress, like
Yeah.
squeezing the surface.
Exactly. Think of it as a built-in squeeze. Fatigue cracks are typically caused by tensile stresses, pulling stresses. If the surface already has this internal compressive stress, it effectively cancels out some of the applied tensile stress.
Making it much harder for a crack to open up and grow.
Precisely. It significantly delays crack initiation and can slow down the growth of small surface cracks. The study mentions combining two techniques, ion implantation and laser shot peening.
Okay, quick explanations. Ion implantation.
That involves firing high-energy ions like nitrogen ions, N+, into the material surface. These ions embed themselves in the outer layer, changing its chemistry slightly, making it harder, and creating that compressive stress.
And laser shot peening, LSP.
LSP uses high-intensity laser pulses. Each pulse creates a tiny burst of plasma on the surface. The rapid expansion of this plasma generates a shock wave that travels into the material, plastically deforming the surface layer and inducing deep, compressive residual stresses.
Okay, both create that beneficial squeeze. Pros and cons of these surface treatments.
Big pros. Increased surface hardness, significant compressive residual stress. Both are very effective at boosting fatigue resistance, especially against crack initiation from the surface.
Cons.
Well, these treatments usually only affect a relatively shallow layer near the surface. If a crack starts deeper inside, they won't help as much.
Right.
Also, there's always a possibility the process itself could degrade other properties if not done correctly. And of course, they add extra, often complex and costly steps to the manufacturing process.
Makes sense. Okay, the fourth and final pillar. Integration of mathematical modeling and experimental verification. Sounds like they're being smart about testing.
Absolutely. This isn't just trial and error. They're heavily relying on computer simulations before and during the experimental work.
Like virtual testing.
Exactly. Using techniques like the finite element method, or FEM, they can build computer models of the titanium alloy. These models can include details like the grain size, the grain orientations, the effects of the alloy composition on properties, and even the hardness and residual stress profiles from the surface treatments.
Wow. Cool.
Then they can simulate how that virtual material behaves under fatigue loading conditions. They can see where stresses concentrate, predict how cracks might form and grow, all within the computer.
Which must save a lot of time and resources compared to just making and breaking stuff.
A huge amount. It allows them to explore way more possibilities and optimize the different parameters, grain size, composition, surface treatment intensity, much more efficiently.
And this guides the actual lab experiments.
Precisely. The simulations help pinpoint the most promising approaches to test physically. And then the data from the real experiments measuring actual fatigue life, examining microstructures, is used to refine and validate the computer models.
Okay, so it's a cycle. Simulation informs experiment, experiment feeds back into simulation.
Right. And a key part of this is developing a fatigue life prediction model based on all that experimental data.
Ah, way to estimate lifespan.
Yes, a model that takes into account all those crucial factors: grain size, orientation, composition via modulus, surface hardness, residual stress, plus the applied stress levels, and predicts how many cycles the component should last. Enough.
This sounds really systematic. Now, the study laid out some specific hypotheses, right? What were their main predictions?
Yeah, they had 4 key ones tied to these pillars. First, they hypothesized that getting those ultrafine grains 1 micron or less with controlled orientation can boost fatigue strength by over 20%.
Okay, 20% from grain control.
Second, they predict that controlling the elastic modulus, keeping it within a 20% range by adjusting the alloy recipe, can raise the stress needed to even start a crack by more than 15%.
Making it harder to initiate. Got it.
Third, their specific surface hardening combo ion implantation plus laser shot peening, they predict that can extend the actual fatigue life, the number of cycles, by over 30%.
Longer lasting parts. Makes sense.
And the big one, number 4, combining all these strategies, the grain control, the alloy tuning, the surface hardening, all guided by the modeling, they hypothesize they can improve the overall fatigue strength by more than 50%.
Wow. Okay, over 50%. That's a massive jump for something like fatigue strength.
It really is. If they can achieve that, it would be a game changer for applications where fatigue is the limiting factor.
So what results are they actually looking for in the lab to confirm these pretty bold predictions?
They have specific metrics tied to each hypothesis. For the grain refinement and orientation, they're looking for that measured 20% increase in the fatigue strength value, like the stress level it can survive for 1 million cycles. And verifying the crack initiation resistance is higher.
Uh-huh.
For the elastic modulus control, they'll be measuring the stress required to initiate cracks, looking for that 15% increase, and confirming longer life due to reduced stress concentration.
Okay.
For the surface hardening combo, they need to measure fatigue life directly in tests and see that extension of over 30%, linking it back to the measured hardness and compressive stress.
Right.
And for the combined approach, they need to demonstrate that overall fatigue strength improvement of 50% in tests, showing that the synergistic effect is real.
Let's dig into the modeling side a bit more. Hull patch, we covered that smaller grains, stronger material, but that fatigue life prediction model sounds tricky.
It definitely is. Because fatigue life depends on so many interacting factors, simple equations often don't cut it. That's why they're turning to machine learning.
Ah, AI predicting material failure.
Sort of, yeah. The study mentions using algorithms like random forest or neural networks,
Why those specific types? What makes them suitable?
because these algorithms are really good at handling complex, nonlinear relationships in data with many variables. They can learn patterns from the experimental results that might be incredibly hard to capture with a traditional physics-based formula.
Okay, so they learn from the data what data goes in.
They'd feed it all the key parameters they measure or control: grain size, D, some index for the crystal orientation, C, the elastic modulus, E, the measured surface hardness, HV, the residual compressive stress, and then the details, the fatigue test itself, like the stress amplitude and the mean stress.
That's a lot of inputs. And the output.
The output is the predicted fatigue life, NF, the number of cycles to failure. So the model basically learns the function, NF equal all those input variables.
Can you give us the 60-second version of how random forest and neural networks actually work?
Okay, super quick. Random forest builds a whole bunch, like hundreds or thousands, of simple decision trees. Each tree gets a slightly different random subset of the data and considers a random subset of the input variables at each split. To make a prediction, it averages the results from all the trees. This makes it really robust.
Okay, wisdom of the crowd, but with trees.
Kinda, yeah. A neural network is different. It's inspired by the brain. It has layers of interconnected nodes or neurons. Information flows through, getting weighted and transformed at each connection. It learns by adjusting those weights based on the difference between its predictions and the actual experimental result, gradually improving its accuracy.
Sounds computationally intensive.
Oh, definitely. Requires significant computing power and expertise to set up and train properly.
And the other modeling tool, FEM. How do they actually build these virtual titanium parts with all that tiny detail?
Right. So in the FEM software, they mention using things like ANSYS or FEDUS. You essentially create a digital mesh representing the component.
A grid.
Yeah, a mesh of small elements. Then you assign material properties to those elements. For this study, they'd need sophisticated techniques. They can model the grains explicitly, defining their size and shape, maybe in 2D or 3D.
Okay.
For crystal orientation, they can assign a specific crystallographic direction vector to each grain, perhaps using data from experiments like EBSD, electron backscatter diffraction, which maps orientations.
Right, I've heard of EBSD.
Then they model the alloy composition by defining the material properties based on the chosen elements and their amounts. And for surface treatments, they apply conditions to the surface elements in the model to represent the increased hardness and the distribution of residual stress, simulating the effect of ion implantation, or LSP.
So you build this incredibly detailed digital twin. What kind of virtual tests do they run on it?
They can do static analyses first, just applying a load and seeing where the stress concentrates, how the residual stresses affect the overall stress field. But the key thing is the fatigue analysis. They apply cyclic loading conditions, specific stress amplitudes, and mean stresses, and the software uses built-in fatigue models, often combined with the stress results, to predict the fatigue life, or track simulated crack growth.
What do they learn from that?
They get maps showing stress and strain distribution throughout the part, predictions of where cracks are most likely to initiate, how they might propagate, and estimates of the overall fatigue life under those specific conditions.
The study mentioned some ANSYS results. What do they show?
Yeah, they gave examples. One simulation apparently showed that as the grain size was made smaller in the model, the stress distribution became more uniform, fewer dangerous peaks.
Which supports the Hall-Petch idea for fatigue.
Exactly. Another simulation visually tracked a crack propagating, showing how it tended to follow specific paths related to the crystal orientation of the grains it passed through, demonstrating how orientation control could potentially steer or impede cracks.
Cool. Okay, shifting from virtual to real. To actually make these advanced alloys and test them, they need some serious hardware. Can you run through the key equipment?
Sure. For making the high-purity alloys with precise compositions, they need vacuum melting furnaces, like vacuum induction melting, VIM, or vacuum arc remelting, VAR. These keep impurities out.
Okay, clean metal.
Then, for controlling grain size and orientation, they need very precise heat treatment furnaces capable of complex temperature cycles and controlled atmospheres or quenching.
Great surface treatment.
Ion implantation equipment, basically a particle accelerator for ions,
Right.
and laser shot peening LSP systems with powerful pulsed lasers.
And for checking the results,
The microstructure.
a whole suite of microscopes. Optical microscopes, OM, for basic grain structure. Scanning electron microscopes, SEM, for much higher magnification, looking at fine microstructural details and fracture surfaces. Transmission electron microscopes, TMM, for even higher resolution, down to seeing grain boundaries, tiny precipitates, even dislocations within the grains.
Wow. Orientation. X-ray diffraction, XRD, is key for analyzing the overall crystal texture and preferred orientations.
And testing the final properties.
Standard stuff, but crucial. Tensile testers to measure strength and ductility. Hardness testers, like Vickers hardness, especially for the surface. And, of course, fatigue testers, machines that apply repeated loads, often rotating bending or axial loading, to directly measure fatigue, strength, and life.
That's a serious lab setup. Now, this all sounds great technically, but let's talk practicality. Why does improving titanium fatigue matter in the real world? Give us an example.
Okay, the classic one. Aircraft engine blades, specifically turbine blades. They operate under intense heat and incredible cyclic stresses from rotation and airflow.
Right.
Fatigue is a primary failure mode. If you can use these techniques to make those blades significantly more resistant to fatigue, you directly improve engine reliability, enhance flight safety, and potentially extend the time between costly engine overhauls.
A big impact on safety and economics there. The study also sketched out a car engine component example.
Yeah, they gave a hypothetical but illustrative case. Imagine using a modified Ti-6Al4V alloy, that's a workhorse titanium alloy.
Uh-huh.
They'd adjust the aluminum, vanadium, maybe add some tin or zirconium, specifically to tune the elastic modulus within that target 20% range.
Yeah, okay.
Then they'd use those advanced Vimvar melting and optimized heat treatments to get grain size down below 1 micrometer with a specific crystal texture.
Right, the microstructure control.
Then apply the surface treatment. Sequence of nitrogen ion implantation followed by laser shot peening, aiming for high hardness and maybe up to 1,000 megapascals of compressive stress.
That's a lot of squeeze.
It is. They'd then perform fatigue tests, expecting to confirm that 50% strength improvement and 30% life extension. The end game. Design engine parts, connecting rods, valves, whatever, using this improved material and process, leading to more durable engines, safer cars, longer vehicle life.
That really brings it home. The study also had some tables comparing their fusion technology to what's already out there. Right.
Yes, useful comparisons. They essentially argue that while existing methods address what's the problem like grain refinement or surface hardening, their integrated approach is designed for synergy.
How so?
For grain control, they're aiming for both refinement and orientation control to maximize crack initiation and propagation resistance, maybe better than just focusing on size. For composition, it's about precise modulus tuning for fatigue, not just general alloying.
And the surface treatment.
Combining ion implantation and LSP is meant to leverage the benefits of both maybe hardness from one, deeper compression from the other, for a greater effect than either alone. The overall message is that the comprehensive, multi-pronged attack yields a predicted 50% improvement, whereas individual existing techniques might typically give, say, 20–30% boosts.
So the whole is greater than the sum of its parts.
That's the hypothesis they're testing.
And they broke down the expected contribution of each part in another table.
Right. Just the ultrafine grains, 1 emitters, maybe 22% strength increase, 18% life extension. Just orientation control, 15% strength, 12% life. Just the composition modulus tuning, 18% strength, 15% life. The surface hardening combo alone, 25% strength, 32% life.
Okay.
But putting it all together in their fusion technology, that's where they expect over 50% strength improvement and over 30% life extension, showing that synergistic boost.
That really paints a clear picture of their strategy and expectations. Okay, let's try and wrap up this deep dive. What are the absolute key takeaways we should leave with?
I think the main thing is this study presents a really smart, comprehensive strategy. It's not just one trick. It's integrating microstructure control, careful alloy design, and advanced surface treatments, all guided by modeling.
Aiming for a big leap in performance.
Exactly. A significant enhancement in the fatigue strength of these already strong titanium alloys, potentially overcoming limitations of past approaches and making a real difference in demanding applications.
And the potential for this to hit the market relatively soon, that 2025–2026 timeframe, is pretty exciting.
It really is. If they succeed and scale it up, we could see the benefits in terms of safety and reliability in aerospace, automotive, medical fields within the next few years. Safer planes, longer-lasting cars, and implants. Tangible benefits.
It's incredible how much science and engineering goes into the materials we rely on every day. Definitely gives you a new appreciation. Okay, final thought for everyone listening. Think about this integrated approach. They're combining multiple techniques to tackle one specific material property, fatigue. Where else could this kind of thinking apply? How might combining different strategies, maybe even from different fields, lead to breakthroughs in other material challenges or even other complex problems entirely? What synergistic effects are waiting to be discovered?
That's a great question to ponder. The potential is huge. And if you want to explore this specific research further, definitely check out freetogear.com for the details and related work.
Lots to think about. Thanks for joining us for this deep dive. Until next time, stay curious.